Hi, this is Ari Everett for CSC120 in the fall of 2023. This is my video demo for demo number 7, the final microprocessor, demonstrating updating the ALU with a custom 8 function unit, along with adding a control module. On the left here is the lab report. On the right is Logisim. This is the final product here. I went through and did the tasks 1, 2, and 3 here, helping check myself along the way. This is my worksheet and my K-maps to create the control module. And then down here were the video assignments and portfolio. This is a 2-part video series, 2 different videos. I completed the first one already in a separate video. This one here is for the microprocessor control. So just a quick overview on the Logisim side. We were given this from the professor. We're to demonstrate we can operate in this and then update this ALU, which only has 4 functions and a 2-bit selection for the 4 functions. This is the sub mechanics of the ALU Mini, and then this is the device version of it. I copied that over and created this with the 8 functions and the 3 bits necessary to create 8 different combinations in binary to output those. These here, I chose bitwise functions because I thought they would be the most straightforward functions and create simple sub-assemblies you can see here. And then I copied over the microprocessor, updated the ALU, added the select modes here, and then worked the logic similar to the design algorithm process we did for sequential usance by looking at this sort of state diagram, you could say. It shows our D flip-flops, create the next state tables, Boolean logic, and then build them out over here. So high-level parts are the control module, which has the state memory with the D flip-flops, the next state logic for each of those things we wanted to automate, and the address generator, which we can pull from in state 1, pull from in state 2, go through the A route, and then state 3 writes it to RAM. Back to 1, that was from ROM B. And then down here is the microprocessor and its different parts. The processor here all along the top, processing through the ALU, then to our accumulator, buffs out, and data bus, important, brings it down to our memory RAM for storage. And then back up, the address decoder will choose to read from this along with these here and circles through. So essentially what we did was, instead of in the microprocessor here where there are manual switches, you can see every single manual switch we have created logic for in our control unit to automate this rather than manually having to do it ourselves. The only things that we need to select in our data path control model here, you can see, is the external signals, which are the start, the clock, which we can just set to on and have it run, loading the ROM with different data that we want, and then of course the select what we want the operation to perform. So let's go through that and let's make sure we answer these questions here. First, also a 2-stage operation and store it to RAM 7. Then we'll use RAM 7 and do a different operation and store it to RAM 6. So let's do that. First off, we'll click this on. If this is off, you can see up here, right here in the D flip-flop control module, it stops there. So let's turn that on. ROM 0 here is 1, and then ROM 1 is 2 decimal, 0010 and 4-bit binary. And then we'll have the address selector state in state 1. You can see 0, 0. Be careful because these D flip-flops are ordered from least significant to most significant bits in the state code that it is. State 1, 0, 1. Let's pull that from, actually we'll leave that at 0, ROM 0. ROM and RAM down here, the numbers after it signify in decimal the address location of them. So ROM 0 is 0 here. So we'll leave this at 0. State 2, 1, ROM for ROM 1. And then state 3, write to RAM. Let's put that to RAM 7, which is 4 plus 2 plus 1. And then let's go ahead and add them together. So we should expect an answer of 3, which would be 0, 0, or it's actually represented in decimal here. So let's go ahead and run the clock. Actually, I'll run it very slowly here. You can see right now it's pushing the information through. First, it pulls in the 1 and puts it through B, and then it puts in the 2 and puts it to A, then the accumulator, count buffer, down through our data bus, and it stores it in RAM 7. So we expected that 3. Great. We'll pause and go to the next step here. Let's take from RAM 7. So let's go 3, and we'll use one of the new functions, a bitwise OR. So we'll take from ROM 7, and we will OR it with ROM 0, which is 1. So any of these numbers could be anything we want here, but let's go ahead and pull from ROM 1. Actually, let's make it more fun. I'll just do ROM 3 just for example. So 2 plus 1 is 3 here. And then we'll store this to 6. So that's 4 plus 2 plus 0 would be into ROM 6. So what is the answer we will expect here is, oh, we need to select 4, 0, 1, 2, 3, 4. For bitwise OR, it takes the individual digits in the same position of each and ORs them with each other. So 7, or 3, here is in 7, 0, 0, 1, 1, ORed with 0, 0, 0, 1. Anything ORed with itself is going to be 1, so it should come out to 3, and we'll put that in RAM 6. Let's go ahead and run that. About 4 full clock cycles later, we should see 6 here populate with that 3 number. Great. Next, discuss the path control model. Data path control model. Identify components of that model in your circuit. Like the input data comes from the ROM. Okay, so here is the slide from, oh man. Sorry, getting over this nasty cold. So input data, essentially before the microprocessor, the control module, we just had input, everything on the right, input, data path, and output. Now we created external signals, which is us selecting the function and clicking the ROM and start and stuff. The controls, which is up here, control signals process through this logic to select automatically what we need at what state, and then data path sends out the status signals, basically where the data is in that point in time, and then this logic will then process to determine what state it's in again, and this kind of loops until we get to the final stage of data output. Data input would be the ROM or the RAM, depending what we select here in state 1. Data path is, call this the data bus, that the data is moving along to go to all the parts of the unit, as well as these data buses and wires here for it to process. Output data is, of course, just our RAM, because that's where we can only write things. Okay. Status signals, again, is on the data bus, just telling the control unit where in the process we are to help it confer with the control, which is up here, the logic in which state to put it in. So 0, 0 here, I'll make this 0. You can see we're all back to state 0, which by our table here is idle, right? And this is what it's doing in idle. It's nothing. And then we can go to the next one is like B, 0, 1, so 0, 1, that would be the next state, and so on and so forth. 1, or then 1, 0, and 1, 1, 0, 0. And external signals, so I wanted to talk about control signals, that a control signal is push this through the tunnels to where the switches used to be, and now they are tunnels. So that's essentially what we've done. And once we created the control module, is replace any of those manual switches that we clicked before with as many tunnels as we possibly can. And that's pretty much it for how the control module works with the data path and control model. Finally, show the K-maps. So I mentioned the design process for all this. This is my top down on how I figured this all out. So for the address regulator, you just look at the addresses here. We don't care what's an idle, right? So that's actually why I have this idle here. And the address generator here is this fourth output, which it doesn't need to be an idle, so we didn't need any logic there because everything is don't care. And then back over here on the left side, address is 1, and then we get Q1, Q0, and that is the logic for it. Q1 and Q0 here, you can see in the address generator, goes through this data bus and decoder to select the state that it's in. Address here, 2, and so on. Now, here are the other logic tables. So here are D1 and D0. D1 was given to us here. We came up with D0, or I came up with D0. You can see the logic here, essentially. So D, for example, D1 is Q1 XOR Q0. So D1, Q, so Q is XORed with the Q of D1 and the Q0 of D0 flip-flop. That is correct. There's 1, 2, 3, 4, 5, 6, 7 more squares, and that relates, or K-maps here, and that relates here to the 7 different next state logics that we have here. So for example, let's take enable here. Enable was like the enable B button, which is right here on the processor. So enable B was from this map where you load B, and that would be a high, and only high on that point. So 0, 1, X, fill the K-map out, derive the Boolean equation, and put that there. Rinse and repeat for the rest. And that is my microprocessor. Thank you very much.